Good afternoon, all. Welcome again to Samvad. Today we have the third of the namely 5G verticals and rollout. Today's speakers are Dr. Anand Mukhopadhyay and Dr. Praful from Mathworks, who will be speaking about artificial intelligence for wireless communications. Professor Priyanka Das is the session chair for today's talk. Professor Priyanka is currently an assistant professor here at IIIT-Bangalore. She received her PhD from IIIT-Bangalore in 2018. Her research interests lie in the areas of spectrum sharing, physical layer security, and intelligent reflecting services. So without any further delay, let me hand over the stage to Professor Priyanka.
Thank you, Nikhil, for the introduction. Now, let me introduce formally our speakers. First, I want to introduce Dr. Anand Mukhopadhyay. Dr. Anand Mukhopadhyay is an education customer success engineer at Mathworks. His role is to work with the education and students across India for effective use of Matlab and Simulink in their curriculum and research. He has interest in addressing various applications using AI methods and HDL workflows. Prior to joining Mathworks, he worked on energy efficient architecture for computing applications during his PhD at Indian Institute of Technology, Kharagpur. He has a master's in the specializations of VLSI design and embedded system from NIT Rourkela and BTech in Electronics and Communication Engineering from Techno India College of Technology, Kolkata. Next, I want to introduce our second speaker, Dr. Praful Pai, who is associated with education team at Mathworks India, where he primarily works with academia in India towards making STEM education engaging and accelerating research using Matlab and Simulink. He completed his graduate studies in biomedical engineering from Manipal Institute of Technology and his MS and PhD from the Department of Electronics and Electrical Communication Engineering at IIT Kharagpur, focusing on non-invasive blood glucose monitoring using photoacoustic. Prior to joining Mathworks, he was an R&D engineer and later a research scientist at National Brain Research Center, Gurgaon, where he worked on developing an MRI brain template for the Indian population. He is passionate about learning, teaching, and research in multidisciplinary domains involving instrumentation, signal processing, statistics, and of course, machine learning. With this, welcome the two speakers in today's Samvaad-Talk in IIIT-Bangalore online mode. Thank you. Over to you, Dr. Anand.
Thank you very much, Professor Priyanka and Professor Nikhil. So we also have Nikhil from our team as well. So in addition to Praful, Nikhil and Devarpita, they have joined here. So Nikhil Sonavni and Devarpita Sinha. So yeah, hi Nikhil. So they will be helping me in assisting some of the queries.
Wonderful.
The participants have.
How are you doing?
Devarpita.
Yeah.
Okay, I am very fine, doing fine. Good to have in your have you in this session.
Yeah, good to see you too.
Thank you.
Yeah, over to you, Anand.
Yeah, thanks Devarpita, thanks Nikhil. So today we are 4 people here. So just to give a brief of some of our current interest areas. So I have done my PhD on the broad domain of VLSI design and have worked on some AI related applications, although not on wireless communication, but other AI related applications. And similarly, Praful Praful, would you like to say?
Sure. So thanks, Professor Priyanka, for the introduction, and thanks to the Samvaad team for inviting us here. So as you already mentioned, my background is primarily in signal processing and communications, and my area is the areas that I've primarily worked on are biomedical engineering related. But I have I'll maybe try assisting this by approaching this from the AI applications point of view, and let's see how we can help communicate how AI can be used in wireless communications.
Yeah, thanks, Praful. So today's agenda will be like, we will initially give an introduction and why we are going to learn about AI in the wireless domain, and then go over the workflow, which is from data preparation to AI modeling, then simulation and test and deployment. So irrespective of any application, this workflow for AI remains the same, and we will try to map it with one of the applications in wireless domain, like spectrum monitoring, where we want to monitor or sense the type of signal, whether it's a 5G signal or an LTE signal at the output, a kind of AI classification problem. And finally, we will discuss some techniques on some interoperability as well. So in case people are working on multiple frameworks, how they can leverage it. And to summarize, we will discuss on some getting started resources for beginners as well as those who are experts in wireless communication, how they can leverage more and more resources towards doing some new projects or other things as well. So in the first slide, the question is like, why now? So is it a correct time to introduce AI in the wireless communication space? So first of all, we have seen that AI has been used massively in different applications involving image processing or signal processing or audio processing, natural language processing, and many applications related to those fields. But it has not been used to that extent in the wireless communication space compared to that, although it has started. So, but currently, because the complexity of the wireless systems is increasing with time, okay, so the number of parameters which are involved in terms of optimizing those systems is also increasing. So that relates to the complexity, and that becomes a complex problem. And whenever there is a complex problem, it is often difficult to hand code the algorithm. So the algorithm or hand coding the algorithm becomes a challenging task in itself. So in those cases, if we can use AI, okay, so to use some data, okay, to model those algorithms. So instead of hand coding those algorithms, if we can model such complex systems, that becomes a relatively simpler task. So that is one primary reason why it is time to use AI in the wireless communication space, because of increase in system complexity. And it can contribute to network simplification, improve performance as well, and better spectral efficiency and so on. So this is one example. On the top, you can see where we are trying to monitor a spectrum of signals. So for that, we need to understand two workflows. So one is the workflow involved in training, followed by the workflow involved in the actual inference process. So if we consider about training, then we need to know or understand the data. So whatever the application or whatever AI application we work on, we usually talk about data. So in this case, we need to understand the signal data or the 5G signal or the LTE signal, the nature of the data. Secondly, we need to transform the signal into an appropriate format. Okay, so why appropriate format? Because whenever we are considering any AI model, which is the second stage here, so at that stage, every model will have its own characteristics, starting from the input layer to the output layer. Okay, so the data should fit or should be able to pass through those machine learning or the deep learning training models. So that is why we need to transform the data accordingly. Then once the training is done, we can use the trained components. So, or you can say the trained parameters in the inference during the actual inference. So this is a classification kind of problem where we are trying to classify certain sets of signals. So we can use the same network, use the trained parameters, and pass the same signal through the same kind of transformation that was done earlier to get the classified result. So this is a general workflow. And it may include machine learning, it may include deep learning, or some applications may also include reinforcement learning workflow. So these are three subsets or three types of AI related algorithms. Now coming to some examples of AI in wireless communication. So one is the spectrum sensing and signal classification, so which we will try to cover today. So this is a spectrogram of the signal, which shows us the time frequency characteristics. And here you can see the labeling. So these are the regions for the LT signals with a slightly lower frequency, and these are the NR 5G signals with a higher frequency. Okay, so this becomes the kind of transformed signal or the transformed data which will be used to do such things. Similarly, there can be other problems like device identification, where we need to identify whether the signal is sent from an authorized authorized transmitting area or by some unauthorized device. So how to do that? That itself is an application. Then application on digital pre-distortion. So this is an important application in wireless communication, where people follow conventional algorithms to do the DPD, so that we can get a better spectrum at the receiver end. Then comes channel estimation. So Professor Priyanka was mentioning that she's interested in channel estimation, beam management, and channel estimation. So how to predict those channels? So again, we need to understand or generate those data, a lot of pilot signals, and try to interpolate them, and finally train to get a correct estimation of the channels using a loss function, or which is a kind of mean square error in this case, and we can predict those things. Then comes localization and position. So to find the true location of a room, okay, so that is another kind of application. Or transceiver design. So one important point is that these are like 6 applications, and whenever a person will be working on any of them, they need to have a thorough understanding. So not just a high level understanding, they need to understand it in more details to understand how the data is generated, or what kind of data are required, because that is a very key step. There are examples in our page related to the applications that were discussed. So some examples can be readily used to get started. So in case you are working on related areas, so the example pages will be very beneficial. Now coming to what is artificial intelligence. So just to give a brief background. So any technique that enables machine to mimic human intelligence, right? So we as a human being, we have our brain with lots of neurons in it, and it can do so many complex tasks in parallel without we even knowing what we are we are doing. So instead of, yes, we have so many sensors which are sensing the environment from our eyes or from our skin and so on continuously, and these are the signals which are sent to the brain to process and do multiple activities voluntarily or involuntarily as well. But if we want to mimic such tendencies into a intelligent system or machine, so that itself is termed as artificial intelligence, which is inspired from the human intelligence. And machine learning is just a subset of AI, where we use some standard statistical methods, algorithms to learn tasks from data, okay, without programming or without writing handwritten code. So that is one subset of AI. And deep learning is another subset of AI, and even as a superset, or not superset, another subset of machine learning, or sub-square set, you can say, of AI, where we have some specific models falling under the category of neural networks, okay, which eventually go to deep neural network. And these models are quite complex in itself. Okay, these models are quite complex in itself, and to run these models, we again need a good amount of hardware. So if you see the time axis, so AI was coined in the year 1950 itself, and machine learning got more prominent in different applications in 1980s. However, because we didn't have such high-end systems, deep learning was not able to, it took time for deep learning to be used in multiple applications. But from 2010 onwards, because of high-end GPUs or even good CPU and other cloud clusters which are available to the users, deep learning got a lot of prominence, and people started exploring these deep networks with lots of data to get better results as well. So we will be discussing some subsequent slides also, when to use machine learning or when to use deep learning. So that is an important issue. Now, going through some basic terminologies which probably you will be knowing if you have started working on AI. But if you are new to it, it is good to understand the different types of machine learning. And so one is the unsupervised learning process or clustering. So this is a kind of process where we only have the data with us. So suppose these are some x5 coordinates, and we have plotted these data here, and we can see that depending on the values, these data fall under different regions. So we can cluster them. So there are different clustering algorithms which can cluster the data set into categories based on the characteristics. So in this case, the cluster is that we have 3 such clusters, and it is divided in this way. But in case of supervised learning, we will also have the labels along with the data point. So it is not only the data point, but what this data represents. So suppose this first data represents a lower value, okay, maybe low, medium, and high. And using that information, we can use supervised learning algorithms, which are again better, because if someone has the labels, they will be able to model a better learning algorithm, or rather than better, I would say easier compared to the unsupervised learning process because of the lack of labels. And again, this can be categorized into 2 categories: classification and regression. So classification is when we are trying to classify certain things. So in today's example, we will try to classify the type of signal, okay, whether it's a 5G signal or whether it's an LTE signal. That's a classification problem. However, the channel estimation problem, okay, where we want to estimate certain values, so that will fall under the category of regression, where we need to estimate a continuous time value in itself. Now, these types are same for deep learning as well. However, the difference is that in deep learning, so there is a term known as feature extraction. So that is not necessary. Okay. So by feature extraction, I mean to say the data can be in various formats. It can be a numeric data, it can be a signal, it can be in text format, or it can directly be an image. Okay, but depending on the type of deep neural network, we can just send the data in that format instead of extracting features out of it. So in machine learning models, essentially we need to extract some useful information, which is known as feature extraction, and then send those features to the ML models, which will be of lesser complexity compared to deep learning. But however, deep learning networks can directly take the raw data as an input and process it to extract the initial feature. The two broad examples is like CNN or convolutional neural network. That is a very good deep neural network for processing images. And if you say RNN or recurrent neural network, that is a very powerful network to process time series data or signals directly. Now, Mathworks. So our tools are, we have different toolboxes, and the purpose of each toolbox is to enable certain things which actually aligns with the wireless with AI domain. So there are toolboxes which helps to cater to the wireless domain and as well as cater to the AI domain. So we will try to discuss how it can be used on a general case, on a general way, and how it could be mapped in specific applications too. So here are a couple of examples. So one is on the DPD, digital pre-distortion, where we have used neural network, neural network to predict the DPD, and the result here is improved performance. So at the output, at the receiver output, we can see a better spectrogram. So the red one is the neural network one, and the blue one is the conventional algorithm using a memory polynomial. And when we are not using any DPD is the yellow one. So using the neural network for DPD has given us better performance. So this is one example that is there. Second is again on channel estimation or beam selection for, again, neural network is used for beam selection, and deep learning is used for estimating the channel out here. So just to map the same examples to the workflow. So initially we need to collect data from a real power amplifier or using the test instrument hardware. So once we have the data, we need to train it using neural network in this case. And once the training is done on the simulated data, we need to test it with some unknown data set. Okay, so using the hardware. So the so we whenever we are collecting the data set from the hardware, so it is to be noted that although we are collecting it from the same hardware, we should not use all the data to just to train it, because there has to be some portion of the data which is unknown to the model. Okay, so only when we are getting good result in the testing set, we can say that the network is well trained, and we can look further on more optimization or more optimization of the network, like doing pruning or quantizing the network to make it more compact, which will eventually help in deploying into an end target like FPGA. Similarly, the workflow remains the same. If we are talking about channel estimation, again, we need to understand the type of data to be generated. So if 5G signals are there, so we need to generate such signals, and we need to understand the type of impairments or that can corrupt the data. So taking all that into analysis, we need to have a good data set. Once that is done, we are going to the next stage of modeling the AI or modeling the algorithm using the AI techniques. And once we are satisfied with the simulation and test, we can generate the code. So code generation is another aspect that is there, which can generate the code towards deploying to the corresponding hardware. So the thing to remember here is the 4 steps, starting from data preparation, AI modeling, simulation and test, and deployment. As an example, let's now start looking at all these 4 steps through an example where we want to monitor a wide band of spectrum for spectrum sensing. So this is a kind of classification problem and also a supervised classification, because we will be knowing the labels of the signals. So if the signal is a 5G signal, it will be labeled as 5G, or if it's an LTE signal, it will be labeled as LTE. And that can be done using Waveform generator app that was started in 2018 B release, so which is a very useful app to generate signals of any type by mentioning the type of parameters, and you will be able to get the signal. Okay. Second, we need to calculate the spectrogram. So the reason here is that we will be using a type of neural network which takes in image as an input. So in this case, spectrogram is a kind of an image, so we cannot feed the signal directly here. So that is the reason we need to calculate the spectrogram of the signal, which will essentially contain the time frequency information in it and could be used further. And we need to label the pixels of the spectrogram. So once we have the spectrogram with us, so whether it's 5G LTE or noise component, so that labeling has to be also done. And finally, we go to the second step of AI modeling, where we need to choose a deep neural network. Okay. It can be an existing neural network, a pre-trained one which has been already trained in multiple images of different type or for a different application. But because it has been trained on multiple images, it has some general characteristics in it which could be used. So that existing network could be used with transfer learning. Also, there are networks like DeepLab V3 with ResNet 50, which has been successful for semantic segmentation applications in image processing, and could be used for spectrum sensing here as well. So once this is done, the optimization of the neural network itself. So the entire problem will have many different kinds of optimization involved in it. But when we are talking about optimizing the deep neural network in itself, so there are hyperparameters involved in each neural network, and it is very difficult process to hit and trial. So with experience and intuition, people may able to change a few of the hyperparameters, maybe like the loss function, the hyperparameters which is influencing the loss function, or like the learning rate. The learning rate is one common parameter. So whether it should be high, low, medium. Okay, but there are many such hyperparameters. So to optimize the network in a systematic way, we have like this experiment manager, okay, where we can set the range of different hyperparameters, and the experiment manager will take its own time to give us the best result based on the metric assigned to it. So once that is done, again, the important part, we have to test it with synthetic signals or with captured real-time or over-the-air signals. Okay, we can do it using SDR hardware, which can be connected using communication toolbox support. And once this is done, this is an iterative process. We can then assess and understand where we can improve. So maybe, or not maybe, so most often cases, going back to the first step itself. So trying to improve the data or the training data. So maybe doing better labeling of the training data, or mixing the synthetic data with real data as well. So next in the data preparation process. So coming to the example of spectrum sensing. So the spectrogram is labeled here, we can see, and there are ways to generate these generate more data from this synthetic label as well. So using networks like GAN or generative adversarial network. So this is again a deep neural network whose purpose is to generate new data set. Okay, so this is one way to increase the generation of synthetic data for from a general point of view. Okay, but for wireless communication, we have this wireless waveform generator app. So in this app, we can generate 5G, 4G, WLAN, and custom modulation signals as well by selecting multiple parameters. So all the parameters which are relevant for generating such data, like the frequency range or the channel bandwidth. Okay, these are few of the parameters can be set here. So there are different modes here, and where we can mention the modulation scheme, and we can add mention the start symbol, the length, and many other parameters. So people in the wireless communication research area will have a better understanding of all these parameters and which parameter are important and what range should be chosen. So with that understanding, we can generate the data, and we can very quickly see the spectrogram of the data, and also the code used to generate that thing. So though we are doing it in a graphical user interface fashion, we can also get the corresponding code out of it, so which can be maybe reused and could be used in generating more such data by changing parameters. So this wireless waveform generator is a great way to generate lots of synthetic data. Okay. However, we can also acquire live data directly to Matlab. Okay, using SDR or the instruments, transmitter or receiver signal instrument. So here we see some of them, like the ones related to SDR are the RTL SDR, Pluto SDR, Zinc SDR, or the USRP. So very easily we can receive real-time signals and probably add it to the synthetic data set to make it more robust. And to do that, we need to do an additional step, because these are external hardware components. So we need to just add the get hardware support package for the respective hardware. Okay, or either by typing the support package installer in the command window, we can generate the we can install the hardware. So in this case, if it is an Adalum Pluto SDR, then just by going through the next steps and connecting it to the computer, the corresponding hardware support package will get installed, and it will be ready to acquire signals or the real signals into it of the desired frequency. We can also connect it to the RF instruments. So like the signals that are generated here, the baseband signals generated here could be sent or downloaded to the signal generator as well. So there is instrument control toolbox which helps us do that. And likewise, if we want to capture some signal and analyze it, so we can use retrieve those IQ baseband data into Matlab for analysis and perform visualization and measurement into it. So there are basically two ways in which we are dealing with data here. So either we are capturing real data or we are creating synthetic data, okay, and then making use of both of them in the analysis process. So we spent some amount of time in the data generation preparation process, but to be honest, this is the most critical step or the most important step. And just to give an example, so on a different note, so there is a researcher known as Andrews Karpathy. Andrews, so I'm not pronouncing his name correctly, but he is currently working in Tesla. And earlier he quoted that when he was doing his PhD, so he spent a very little time in the data preparation aspect, right? And more on the AI modeling. So at least it can be like 15% to 85%, 15% time on data preparation and 85 on AI modeling. However, when he's working in Tesla to design those automated driving vehicles, okay, which requires a lot of image data and a lot of processing, almost 70% or 75% of the time is spent on creating the data set for that problem. So whenever there is a complex problem in hand and whenever there is deployment involved in it, so when we want to finally get good result after deploying it on the test signal, the first step itself is the most critical thing to understand the problem and generate or create suitable data out of it. However, next we move on to the AI modeling aspect. And in the AI modeling aspect, the second step, there are many algorithms. So whether it's machine learning or a deep learning or reinforcement learning, whether it's a regression problem where we want to predict certain things, or whether it's an unsupervised learning, we do not have the labels, okay, or using Bayesian optimization techniques, we have to create that model using the data. So either we can do it by scratch or we can make use of pre-built models or pre-trained models. So these are some of them like AlexNet, GoogleNet, VGG, SquizNet, etc. So these are image classification models. So each of the models are trained on a lot of or millions of images, and we have the final model available for everyone to use to reuse. So that is why it is known as pre-trained model, and we can use it in different applications of similar type. Then there are reference examples on object detection, semantic segmentation, signal and speech processing, and many more. Especially on semantic segmentation, where we want to it's kind of segmenting a portion of the image. So this is related. This relates to the problem of the spectrum sensing. So in the spectrum, we have different regions. One region corresponding to the LT signals, another to noise and 5G. So if it can be related to the semantic segmentation problem in the image processing domain, where we want to segment certain portions of the image. Okay, so if we want to use this the way semantic segmentation is done in the spectrum sensing problem, we need to map that data again into similar way and use models which support these kind of things. So coming to the next slide, so we talked about where we can get the data, either the synthesized data or the real over the air signal data. And once we have the data set, it is also important to understand what kind of models should we use, because there are so many. So this is one graph which gives us a better understanding to do that. So x-axis is the domain knowledge and y-axis is the data set size and quality. So in case we have good domain knowledge on the application we are going to work, then we can actually derive certain useful information out of the data. And that will eventually help us have a smaller feature vector. Means the data set size will be smaller compared to the raw data. And if we have such information, we can use simpler models like machine learning models with many features. So this is one extreme. The other way, if we do not have much domain knowledge about the signal, then we have to work with raw data. But in that case, we can use deep learning, but we need to collect a lot of data. We need to have a high number of such data sets. So in case we are working with IQ signals where which can be captured and a large data set can be made, we can use, we then go for the deep learning technique. And there are in between ways to pre-process the signal, generate the time frequency maps. Okay, so suppose in this case, in today's example, the spectrogram itself is a kind of pre-processing step. So from the signal, we are generating the spectrogram to get the time frequency map, and that acts as an image to probably a CNN network, which is good for processing images. There are powerful techniques like wavelet scattering also, which can again extract a good amount of information from the data, and that could be fed to the corresponding AI models. So this will give some understanding of how to approach the application. So data set size versus domain knowledge versus compute resources. And we have multiple places or support which helps us to accelerate the workflow, because when we are talking about deep learning, so it is no doubt a very computationally intensive process, and training itself will take a lot of time. So people tend to use the clusters or the cloud resources by AWS or Azure, okay, or the NVIDIA Jetson GPUs, but they can run the training algorithm at a much faster rate. Okay, so to do that, we need to convert the existing algorithm to the corresponding code. So for example, in NVIDIA, which supports a CUDA code format, so that code generation is supported. So it could be, it is supported by our tools. So that code generation will help the user get the CUDA code, and it could be run onto the NVIDIA device on a much faster speed to complete those processes. So GPUs, clouds, data center resources. So all these things could be used without having the knowledge of specialized programming. Okay, so that is where we have the code generation support for these different hardware. Now, when we are talking about training, so we can either use existing deep neural network or like the Deep Lab version 3 with ResNet 50, which is a powerful one for semantic segmentation, and use transfer learning to it. So this is another app. So just like the Waveform generator app, this is the Deep Network Designer app, where we have just loaded the pre-trained model, the Deep Net, which is a CNN model, a very large CNN model. And using transfer learning, we can learn certain parameters. We can learn certain parameters on some of the portions, and the remaining parameters can stay as it is. Okay. So this is why transfer learning is useful. If you ask, then because it is actually saving us a lot of time, and also helping us to get a model, derive at a model without having a large data set, because creating the data set, though challenging, but when we have models which has been trained on similar kind of patterns, similar kind of images earlier, so using those models and then doing some transfer learning with the new data is a helpful process in saving the overall time. So that is the reason we do this. And once the transfer learning is done, then we have to go to the experiment manager. So in the experiment manager, these are the hyperparameters, and this is the metric like the pixel accuracy. Okay. So this will run different models. So in this case, there are 30 such models, and we can see the pixel accuracy to be 94%, which is the highest among the 30 models. So which will give us the optimized model, okay, within a range of hyperparameters. So this is another useful thing to optimize the neural network further. Next, we talk about testing and validation. So once we have the model, we need to test it on a new signal. So if this is a new signal, so the transformed version of the new signal, which is the spectrogram, can be fed to the pre-trained model. So the training was done earlier, just using the same architecture with the parameters. So in this case, these connections between the input and hidden layer are known as the parameters, the weights, and there will be biases, weights, biases. If it's a CNN, there will be some more parameters like the filters, the filter coefficient. So all these values are fixed, and the signal has to just go through the process of either multiplication, addition, and so on to get to a result. And in this case, it is a classification problem, so it will be classifying the type of signal. So this testing can be done with a mix of signal, either with the synthetic signals alone or with the real-time captured signal alone, or then making a combination of both the things and see how it is performing, how the test result is we are getting based on the confusion matrix. Okay. So what is the confusion matrix? Confusion matrix gives us the idea of the true class versus the predicted class. So here it is a 3 by 3 matrix because there are 3 classes, 5G, LTE, and noise. So whenever there is a correct prediction, it will fall under the diagonal. And we see 97% of the time it is predicting correctly. Similarly, 97% of the time noise is also getting predicted correctly, and 87% of the time we are able to predict LT correctly. Okay, so there is misclassification of LT with noise. So 10% of the time the LT signal is classified as a noise. Okay, so from this confusion matrix, we can get some understanding on the data set, like how we can improve this further. So maybe the bandwidth of the LT signals that were used, okay, that is not sufficient to give us the better prediction. So we need some more LT data. Maybe there is data imbalance. So there has to be enough, not only lot of data, but a balance between all the 3 classes as well. So these are some reasons. So this will give better idea, and then we can capture more signals with setting different parameters. And in this case, you can see a LT signal of a larger bandwidth has been captured again, and which will enhance the training data and give us better results. Okay, so capturing data, augmenting the data, and repeating it in an iterative way will give us better results subsequently. Now we discussed about the third step. The final step is about deploying it to any processor. Okay, so that the performance remains is not changed significantly. It remains similar to what we see in the algorithm. So it can be deployed in embedded device, edge device, enterprise systems, clouds, or desktop. So the way to do that is we have a MATLAB compiler and MATLAB compiler SDK, which helps us generate the corresponding code which is used to deploy in such systems. Okay, so there is this code generation workflow, so which helps us to generate the GPU compatible code, the CUDA codes, the FPGA compatible codes, the HDL codes, or the CPU compatible C++ C code to the respective end devices. So this shows 5 lines of code of how the deep learning network could run on the FPGA, so which will be much faster compared to what it takes on the normal PC. So once we have the trained network, so trained network is the trained model, so we can use that trained model object using this command line code and compile it and do the inference or the prediction at a much faster speed on the FPGA itself. So this is for inferencing and predicting the output at a much faster rate. So we have this HDL deep learning HDL toolbox, which is helping us to do that. Then coming to the interoperability thing, so MATLAB and Python can be used together. Either MATLAB code could be packaged to the Python environment, or we can call libraries written in Python from MATLAB. So both ways it can be done. So here is an example which shows we are calling TensorFlow object from the MATLAB live editor space. Okay, calling Python from MATLAB. So the steps are like copying the code into a .py file and wrap the entry point in a function. And once we import the corresponding libraries, we can import the functions towards MATLAB. And we can call the module using these extensions, py.mymodule.mytf code. So the function that is defined here will be called from MATLAB itself. Okay, so this is one simple example, but in case okay, so yeah, so the corresponding API has to be installed in the directory. So Python 2.7, and this is just computing the square root of that using the command window. So summarizing the deployment, so from MATLAB we can use the MATLAB compiler and MATLAB compiler SDK or on the Simulink compiler or the coder products to deploy in different end systems like embedded hardware, desktop web development, in the enterprise system involving the MATLAB production server, or in the Simulink itself. So if the system is built in Simulink, so some of the algorithms that are built, the AI algorithms could be also sent to the Simulink directly for further testing and simulation. So there are some resources. So these are basically communication resources that are in the courseware page. We have one on Digital Communication Lab and a systems introductory course on SDRs. So in case you are teaching similar courses, you can use it. And there are these self-paced courses, so out of which some of the courses which are relevant will be on this related to deep learning on-ramp and the machine learning on-ramp. This will be relevant for people who are exploring the AI space. And there are some on wireless communication on them, a small introductory course which could be used by instructors in their course for their students. So the students can complete this hands-on course directly through the browser and get an hands-on experience whenever the subject is being taught in the same semester, and which will eventually help them do projects. So there are some full courses as well. So on both on deep learning, machine learning available. So these are extensive courses, 14-hour long duration. So this will give better insights and better hands-on experience on some specific set of problems with some mini projects as well. So this is the wireless communication on-ramp, which is a 1-hour duration course, which gives a brief introduction on how one can simulate a basic digital communication link and do pulse shaping, design a pulse shaping filters and design the multipath channels, OFDM modulation, and conclude it. Okay. So there are some training courses. So these are some training courses which are again useful to from the perspective of using AI and statistical measures and in the best ways, in addition to some MATLAB fundamentals and some ways to accelerate and parallelize the MATLAB code. So these are some, there are some MOOC materials as well on the data science space. Or we have a training team in Mathworks. So in case any customized training is needed on the data science AI space, that can also be, that is also possible with our training team. And one resource on the research front. So here we see we have a Mathworks Excellence in Innovation project space. And here we have the problem statements on multiple areas, starting from 5G, AI, autonomous vehicle, big data, and so on. So, so students can, or research scholars who are working on related projects, if they find some interesting project, can work on these projects and then sign up for the program. So one such project related to 5G and AI is on signal coverage maps using measurement and machine learning. So let me very briefly show you the projects page. So this is the Excellence in Innovation projects, and under 5G and AI, there are different projects listed. And this is the one such project where students will find the motivation of the project description, some background materials which are needed to do it, and also the difficulty level. So this one is a master's and above project. So it has some amount of difficulty. Some projects can be done by bachelor students as well. But from this, students can get an understanding, and they can either make a team also and work together on the project with a faculty advisor. So there is one form which is to be filled out here, which where the project title, project number, and project notes are to be mentioned with the name, mail, college, country, department, degree, number of team members, and expected start date. So this is just to let us know that you are interested in working in this project, and once you are able to complete it and submit your initial results, the entire team receives a certificate and endorsement from the Mathworks team as well. So this is a nice way to find some 20+ problem statements on different topics as well, not limited to AI and wireless, but yeah. Finally, the key takeaway that we wanted you to take from today's webinar is to understand the workflow, so the entire AI workflow, and how it could be mapped to some wireless communication applications, starting from preparing the training data, training the network, and testing it with the synthetic or the real-time data signals in Matlab. Okay, so we saw how we can use the waveform generator app to generate the synthetic signals. Using the same app, we can also add channel and RF impairments. How with SDR or hardware connectivity, we can capture over there signals and ways to augment the captured signals with RF impairment, means just combining both the signals, synthetic and the captured signal. Then about pre-processing training data. So pre-processing, or in this case, converting the signal to the spectrogram was the pre-processing step. So also filtering or removing unwanted signals, another pre-processing step. And finally, going to the AI modeling, where we want to train the model on the data to design either using the pre-trained networks and then optimize the model further using experiment manager to fine tune or select the best combination of hyperparameters for the model. And finally, see the results using unknown set of signals, okay, using real signals captured in SDR, and ways to use code gen workflows, SDL coder workflows to deploy it on FPGA for inference. And very briefly, we saw how we can import export networks from other framework as well. So these are some resources, like there are videos and webinars, tutorials, MATLAB Central, which is an open exchange community, and file exchange resources, the on-ramps which I discussed earlier on the hands-on self-paced courses, and some instructor-led trainings which can help anyone start working on their projects and learn more subsequently. So this was primarily the presentation content for today, and we would now like to have some question and answers from the audience, and you can also please do fill the feedback link here. So this is really helpful for us.
Thank you, Dr. Anand. Now we can have some question and answer round.
Yes, I am looking into the chat window now. I see there has been a lot of communication. Thank you. So Praful has answered to most of them. Thanks, Praful. So Praful, do you want to highlight any of the earlier questions which is asked?
So yeah, I think at the very beginning there were a couple of questions on using machine learning or deep learning when predicting range reception with terrain data and weather conditions as inputs. So I think yeah, I think as long as you have good enough data to kind of work with for training the deep neural network, I think that's a good problem to have. And I think one of the project statements that you had on the slide about excellence in innovation program. So if you could go to that slide, that talks about exactly that, I think, or at least talks about on the 5G side, yeah, the signal coverage maps. So I think how can we generate signal coverage maps using a limited set of measurements. I think this is exactly something like a related application. So yeah. So there's Dwikul asks, so apart from any third-party optimization tools on Matlab, so can we use any built-in deep learning tools for solving optimization problems? If yes, how? So Dwikul, can you specify which third-party tools are you? Is it CVX, which you're referring to? I guess I've heard that the most. I guess, yeah. So if you're using CVX, that's great. But there's also the inbuilt optimization toolbox, as well as the global optimization toolbox, which you can utilize. And what would be useful is a good way to get started with that is the optimization on-ramp. So Anand, if you could maybe just highlight that on the browser itself, that would be great.
Yes, let me do that.
So other than that, you can utilize like deep learning for some optimization problems as well. But yeah, I would maybe try out the optimization toolbox, internal optimization toolbox, and then maybe
I'm sharing the product page for optimization toolbox. So this is the starting page, which will give you all the necessary resources to get started, and how you can use the optimization toolbox to model with some document videos and examples. So all of them will be listed here, whether it's a problem-based, solver-based optimization, what kind of solvers are needed to be selected, the setting options, etc., and so on. And on certain applications which are actually using optimization or which is an optimization problem, and so on. And yeah, this is the one page. And the second one, let me share it in the chat as well. And the second one is the Matlab Academy page. So we were talking about machine learning and deep learning in particular, which is available in the on-ramp as well as a full course. But we have an optimization on-ramp as well. So how to use the optimization related functions or optimization related live tasks, which are a version of the applications. So similar to the applications we were discussing earlier. So we have a live task as well on optimization for in a very short time. So within 1 hour, you will get an idea how it is used for certain project on radiation therapy. And maybe then you can map it to your optimization problem based on that.
So does that answer your question? Because okay, sure. Yeah. All right. So in case there are any other questions, please feel free to unmute voiceover or post them on chat. One more question in between which I saw was Anand about what to use when. So would RNNs be better, or would CNNs be better? And how to decide what to use, or especially when you're dealing with signals.
Okay. Okay, this is I can take this question. So this is a very good question, I would say, because when we are dealing with signals, then why are we converting it to a spectrogram and using CNN? So we can also probably use it directly in RNNs as well. So one of the motivation of using CNN is that CNN during the decade from 2010 onward, CNN has been used in multiple applications, and somehow it is giving good accuracy. good amount of performance. So that itself became a motivation of utilizing those CNN pre-trained networks. But again, from a general perspective, one should not restrict to use CNN. RNNs can also be used. And also, the major challenge is about keeping the network size also small, because although we have compute resources, so as we were seeing in the one of the slides, that we want to prune the network prior to deployment. Okay, so once we have the final network and we want to deploy it for inference on some hardware, so to make that inference faster, we need a network which has a less complexity. So that is another thing to be aware of, to assess the network complexity of a CNN or a RNN, because ultimately, if the network complexity is less, then the number of computations will be less, and then the inference time will also be less. So that is another important thing to look at, in addition to the performance which you are getting. So RNNs can also be used directly on the time series signal, or because CNN have performed well in image related problems, we can convert the signals to the spectrogram, and we know spectrogram is a rich has a lot of information, time frequency information, and looks like an image. So we have the signal in the image format, and then leveraging the pre-trained models. But there are many considerations and choices depend on all of these things. So Praful, would you like to add anything here? Or
there is a one more question from the chat box. Is there a default 5G 5-layer model with a transmitter, receiver, and channel which can be used to study high layer L2, L3 functionalities?
Yeah. So
default 5G physical layer model.
Okay, this one. So when you say a default 5G model, like what exactly are you maybe looking for here in terms of?
Dibakar, you can unmute and clarify the question.
So I just wanted to know, suppose if we could have some default parameters. So for example, if I'm not interested in nitty-gritty details of 5-layer, the parameters, are there some default settings which can help me to say do some sort of layer 2 scheduling, not really getting into the underlying nitty-gritty details of setting each and every parameter and stuff like that.
Like, I would say.
Now, for example, in the signal generator, you showed that we have to set so many parameters and stuff like that. Is there a default set of parameters which can kind of, we can use it as a plugin for studying L2 scheduling, for example?
One thing is that some of the parameters will be set by default, and you need to change some of the important or the more relevant parameters before generating the signal. So that is the workflow that is followed in the signal waveform generator app. So, but if I understand correctly, is your question more on generating a 5G signal without mentioning any parameters by default? Or
yeah, I mean, it could just take the default parameters and give me an abstract functionality, basically.
Yeah, I think one thing is, yeah, you could definitely do that. So I am not really recalling an application. I'm not I'm trying to find an example which would be a good starting point for this, but I'm not able to kind of find one. If you could share your email on the chat, then that would be kind of a good point to get started with. Otherwise, I think let me just look over maybe what would be a good starting point where you could do that. But there are definitely like you can definitely do this. That's for sure. Yeah.
So yeah,
Sure.
we another thing, because the purpose of this app is to generate signals anyway. So by default, if you don't touch any of the parameters, you will be able to get the default setting. So that will help you generate one such waveform. And now to generate more such waveform, then you have to either use a function and then maybe use a for loop across certain parameters so that the range remains in the same frequency domain and you can change certain parameters. So that is the way you can generate more such signals. But yeah, that is one thing, but we can look over it separately as well. You can write a mail to us to see.
Sure. Yeah, I think someone's also posted Sudarshan's posted a example outlining this as well. So I think we'd go over that particular example or this one. Look at this. Yeah.
Sure.
Thanks, Anand and Praful. I have a very basic question. Let's say a student needs to start from the scratch into the AI for wireless. What will be your ideal suggestion for the student to wrap it up with 2 to 3 months?
Sure. Anand, would you like to maybe take that one?
So my one suggestion would be, so if the student wants to learn AI and apply it to the wireless domain, so depending on the problem, to understand about the first step itself on the data part. So how the data is being used, whether it's a synthetic data or real data which is captured. Okay, so understanding that data, and second, how the dimension of the data and the type of data. So how it will be processed towards the AI model, because that itself will be a big task and will be actually helping to move to the next step. So before we complete the first process of data preparation and processing, we finally need to feed that data to the input of the next stage, which is the AI modeling network. So that understanding has to be is the one crucial step. And once that is done, the second step is relatively easier compared to the first step. I won't say easier, but second step is to identify what kind of approach should we take, either a machine learning model or a deep learning model or any other model, which model to choose. So that again, next, the tool is helping to create such models using the available workflows, and going forward to the third step of simulation and towards deployment. But yeah, that was one. Yeah, Praful. Yeah.
Yeah. So to add to what Anand mentioned, I think as so if someone's starting off with learning machine learning or deep learning or wireless, so I think I just posted a Matlab Academy link. So Anand, if you could just go to that page.
Okay.
So I think once one is familiar with wireless communications anyhow, and then you'll be using a bunch of MATLAB to do that. What we've also seen is even though people have been users of MATLAB for wireless communications, you might very often you may not really have learned machine learning or deep learning as a subject. So gaining having a course to do that, maybe one aspect that people can take on, look at the mathematical concepts which underlie machine learning or deep learning. And on the application side, so how do you apply machine learning? I think this particular course link kind of outlines everything. So there are on-ramp courses which can help with, say, introducing how you can start with, on maybe the previous page itself, start with machine learning or deep learning itself. And then there are these advanced courses, these longer courses on machine learning with MATLAB or deep learning with MATLAB, which might, again, be good from an application point of view, like if you're looking at a tool to kind of apply this in. And if you're looking at reinforcement learning applications for your communications, then there's a reinforcement learning on-ramp as well. So yeah, I hope that answers it. These would be good if you have, say, some idea of some basic idea of machine learning and deep learning, or you can just try them out. This also outlines some of the applications in detail, but a two-pronged approach where you learn about the mathematical concepts as well as learn about the application part of it, or how you can implement it would be good, in my opinion.
Thank you. Thank you so much. This is a really insightful information to the students and also to the industries. Any further question?
Another thing to add to that, so there is this examples page, which has some examples specific to the wireless domain. So the student may find some of the examples close to the work they will be working on, and they can use these examples. So for example, today we were covering this one. Okay. If I just open this tab, so the entire documentation and the code involved to go through the example is mentioned here. So this is a classification problem and a supervised problem. So in case the problem is similar, they can make use of the existing example page as well. And also there is one solution page. So for AI, I have just AI for wireless. So where most of the resources which are useful are captured in the same space. Mathworks.com solutions wireless communication AI. And again, this points to those examples, the different examples where AI is being used, whether it's for classifying the spectrum, device identification, DPD, channel estimation, and so on. So all these are individual examples. So in addition to the course, and if the students can find the most related example and follow along that side, they can then, I believe, in 2-3 months will be a good time for getting some good results out of their work. And the pre-recorded videos are also there to revise on certain lectures, which comes from time to time. Yeah.
Thank you.
Thank you.
Is there any further question from the audience? Thanks a lot, Dr. Anand and Dr. Praful. It's really an insightful information.
Thank you, Professor Priyanka.
For having us.
And we will be in touch with you in near future whenever we need suggestions and help.
Sure, definitely. And we would request everyone to take some time, maybe It will take around 3 minutes or 4 minutes. So just fill the feedback form, and whatever or one key takeaway that they have taken from today's thing, and any points to improve further, we will be very happy for that. Yeah.
Sure. So the feedback link, I request to all of you, please just the note of that link, and you can fill it up and submit to that.
Okay, let me also paste the link in the chat. Yeah, I've pasted the link to the feedback form. So it will have a certain set of questions. Which aspect of AI workflow, where are you in your AI journey, and yeah, and any other feedback and suggestions from your side.
Thank you. Now I hand over to Professor Nikhil.
Thank you, Priyanka. So thanks again, Anand and others from Mathworks for kindly, first of all, kindly agreeing to give a presentation, and thanks also for the wonderful presentation and your thing. And yeah, nice meeting you all.